Beginning in this lesson, we're going to learn how you conduct your own significance test. And in 9.2, we're going to focus on how you run a significance test for a proportion p. So what's going to end up happening in this video is we're going to learn how you actually find that p-value that we've been using to make decisions and basically learn the whole process. So our first big example of our notes today, me and my friend Larry are hanging out talking, and Larry claims that he is just an amazing soccer player. He is so good, and he says he can make 80% of his penalty kicks on an open goal in soccer. So Larry goes out and he says, hey, I can make 80% of my kicks. I, on the other hand, disagree, and I say, no, Larry, you're not that good. You're going to make less shots than that. So going in, I kind of have the thought that Larry is not an 80% shooter. He is actually lower than that. So we decide naturally that we're going to use a significance test and let statistics help guide our actual decision in who is correct. So we end up taking a random sample of 50 kicks, and a random sample in a situation like this is kind of tricky to manage. Like, how do you get a random selection of Larry's shots? What probably happened is we went out there and just kicked 50 of them and called it a random sample. But we managed to obtain a sample of 50, and we found that Larry made 32 out of the 50, which is a 64%. So that's kind of what's going on in this problem. Larry claims he's 80, but we got 64. And we're going to look at that difference between those two things, 80 versus 64, and make a conclusion based on that. So the first thing we would do is we would establish our hypotheses. And in fact, the hypotheses would have happened before we even got that 64% in the first place. So what we're interested in for this problem, we're basically running a test on P, where P is going to be the true proportion of kicks that Larry makes. So we're looking at what percent of his kicks he actually go in the goal. And then for our hypotheses right here, your HO, your null hypothesis, is always the status quo. It's what we're kind of, our baseline is. And we're going to go into this problem assuming that Larry is correct. So Larry claims he's an 80% shooter, and that's the truth we're going to operate under. But I am looking for evidence. I'm choosing to run this test, and I think that Larry is actually less than an 80% shooter. So when you're setting up your hypotheses in general, HO, you're kind of like propping up an HO, hoping that the evidence will show you that HO is wrong and you can kind of slap it down. So I'm running this test. I don't think Larry's right. So I put, okay, yeah, fine, you're an 80% shooter. And then I'm trying to show that he's wrong and he's actually worse than that. So it's less than 0.8 for the alternative hypothesis. We collect data and we get a 64%. This is going to be our p hats for this problem, our sample proportion. So think about what would happen if me and Larry are arguing. He got his 64%. I would be like, hey, Larry, you got 64. You said you were 80. Clearly, you're worse than you said you were. And Larry, on the other hand, would be like, nuh-uh, I am an 80% shooter. I just got unlucky with this sample. So the two of us would be arguing back and forth over which of us is right, okay? He's like, no, I'm 80. This is just a weird sample. I say, no, it's not 80 in the first place. You're actually worse than that. And that is the argument that we would be having. In last section, we talked about the two explanations for why we didn't get what we were supposed to there. Either there is a difference and Larry's not an 80% shooter, or he is an 80% shooter and the 64 that we got occurred by chance. So the kind of thing we do to solve our arguments, we need to figure out how rare a 64 is when the answer is actually 80. And that is what we will be doing statistics to figure out in this lesson. It's going to involve that sampling distribution stuff we learned back in chapter 7. So before we actually can answer that, we're going to look at conditions for a significance test. Just like with confidence intervals, there are 3 conditions you need to check. They're very similar to what you would do in confidence interval problems. In fact, 2 of them are completely identical. So see what you can remember, maybe pause me and see if you can rattle off your 3 conditions for P problems. You should know that it comes from a random sample. Your data needs to be a simple random sample. And then we also have that 10% condition. I'm not going to make us write why we check these again, but the 10% condition is to make sure trials are basically independent so you can calculate your standard deviation. Then there was the 3rd condition, which in a P problem was called the large counts condition. Now, if you think back to last chapter, I should say, what we did is we plugged in P hat for these problems. We checked these guys right here because we didn't know actual P. When you make a confidence interval, you're trying to estimate P, so you can't plug it in. So that would be fine, and that worked great for us in chapter 8 with confidence intervals because P hat was all we had. Whenever you conduct a significance test, though, you are going into the problem assuming that the null hypothesis is true. Okay, Larry, we're going to assume you actually are an 80% kicker here, and then I'm going to try to prove that you're wrong. So when you conduct a significance test, you go in assuming HO is the truth, and then you look for evidence for this guy right here. So instead of using P hats for these problems right here, why would we use like our sample when we think we know the actual truth? So this is like a little bit of a wordy way of saying when you check large counts in this chapter, instead of using P hats, what you're actually going to use is the P from HO. So the way I'm going to write that down right here, I'm going to put P with a little subscript of O. That means your null hypothesis value. So you still check the same thing, n times P, n times 1 minus P. But when you check them, you're going to use your value from HO, not what you got from the sample. In a confidence interval, we had no choice. That's all we had was P hat. But when you do a significance test, you assume HO is true. So we're going to use the value that we're assuming to be true. Okay? So how would we check these 3 conditions in our penalty kick problem right here? I'm just going to rattle them off for the first 2. It's a random sample, or it was supposedly somehow we got a random sample of 50 kicks. And 50 is certainly less than 10% of all the kicks that he could possibly make. When I check that 3rd condition, what I would do is I would check 50 times, and I got to use my 0.8 for this. So I would check this, and I would check this. This guy is, 40. This will be a 10 right here. Both of those are greater than or equal to 10. So we're good to go. Okay, so we check our 3 conditions before we can run any fancy statistics, just like we would do last chapter. So now that we've established that, okay, yeah, our conditions are met, let's talk about how you would actually figure out what's going on. And as I referenced earlier, it's going to use the concept of a sampling distribution. We go into this problem assuming that the answer is 0.8. I'm going to assume Larry's telling the truth, and I'm going to prove to him that, hey, you're actually wrong when we do this problem. So if the answer is actually 0.8, we learned that P problems look approximately normal as long as that large counts condition is met, which we just checked 2 seconds ago. So we know that P hat, the possible P hats we can get, the possible sample proportions, follow a normal curve right here. So this graph is a graph of the sampling distribution of P hats. These are all of my possible P hats, assuming that the actual answer is a 0.8. Remember what I said earlier. What we're doing when we use statistics on this problem is we're saying, okay, if it's actually a 0.8, how rare is 0.64? Larry says, oh, totally possible, not that rare at all to get a 0.64. I say, you know what, Larry, you're probably not going to get a 0.64 if the answer is actually 0.8. So our graph is centered right here. And this turns into very much a chapter 7 sampling distributions problem. All we want to know is how rare is 0.64 or lower? How likely is it that we get a 64 if the answer is actually 80? So when we look at these graphs right here, the mean of your sampling distribution is going to equal the value that you assume in HO. So it's centered right here at a 0.8. That's what the mean of my sampling distribution is going to be. And then for my standard deviation, if you recall from a few chapters back, or even last chapter, our formula went P1 minus P over N. Okay? So if I look at this problem, I want to know how rare a 0.64 is. And just by the way the picture is structured here, you can tell it's kind of rare for that to happen. But what we would need to do is just calculate it for our problem. Our mean is going to be a 0.8. And then for our standard deviation, I would need to plug in 0.8, 1 minus 0.8, and it was 50 shots right here that we took. And I'll just type that in real fast to tell you guys what I get. The standard deviation is 0.0566 if you round. Okay. So I know the mean of this graph right there, 0.8. I know the standard deviation of this graph, which I just calculated, is 0.0566. And I want to know how rare a 0.64 or even more extreme is going to be, or even lower in this problem. This is just normal CDF, like we've already talked about. If you set up a normal CDF with a lower bound of 0 and upper bounds of what we actually got in our sample, a mean of 0.8 and a standard deviation of what you got right there, and you do that, you should get a p-value of about 0.0023. Okay? So that's the p-value you'll end up getting if you do a normal CDF on this problem. What does that mean? Well, if Larry actually is an 80% kicker, getting a 64 or even worse than that, just by chance, just, oh man, oh, rough sample, I just got a bad luck right there. The chances of that happening are not even 1%. It's like a 0.2%. Okay? So think about that. Larry says he's an 80% shooter. Happened the 64, just bad luck. But the chances of that actually being bad luck are really, really, really low in this problem. So you have two possibilities here. Larry's like, oh man, I just got that fluky sample. I am just so unlucky. But I'm sitting there looking like, really? You got the 0.002 option? No, it's a lot more likely that we were actually wrong about this assumption right here. The center of the graph isn't a 0.8. Maybe he's really like a 70% shooter or something like that. Because if my picture went like this, well, then a 64 isn't so rare anymore. So what we end up doing in this problem, our p-value is so low, we reject Larry. Larry, you're probably wrong. And we go with the alternative hypothesis right there. The evidence was strong enough. It would be so rare for Larry to actually be correct, where it's probably me who's right in this problem. That's how a significance test works. Is it possible that Larry actually was telling the truth and we did get an unlucky sample? Yeah, it is. There's a 0.002 chance of that happening, but it's a lot more likely that I'm right and Larry's 0.8 is just wrong in the problem. And that's how one of these problems works. So hopefully, the more we do with this, the more that starts to make sense to you guys. So when we conduct a significance test, we find frequently something called a test statistic. So what I showed you on the last slide right here, this normal CDF setup with the numbers from the problem is great. It worked, it got us the answer, life is good. But there's a little tweak to how we usually set these up, and it uses a test statistic, which is basically a z-score. So if you remember from a z-score back in like chapter 2, it went value minus mean divided by standard deviation. So a test statistic is basically putting a standardized number to how rare the results are that you get from a problem. So in our penalty kick problem, if we were going to find a test statistic, we'd be finding a standardized value for Larry's 64. How rare is 64? So what you do is you take your statistic, what you actually got. This is like a value when we do a z-score. Well, we got a 0.64. Minus, here we would put the mean or the true value. Well, in this problem, we're assuming the true value is our parameter, which we assumed was a 0.8. And we would put this over the standard deviation of your test statistic, which is that little formula we did on the last page, the 0.81 minus 0.8 over 50. If you actually calculate this guy out, you're going to get a test statistic of negative 2.83. So think way back to when we learned about z-scores. We talked about how most points are within 2.5 standard deviations of the mean. Getting a point like 3 standard deviations away, super rare. So what we could do once we have our test statistic is instead of doing a normal CDF with like a 0.64 and the numbers from the problem, you could do a normal CDF with a lower of like negative 1,000 and an upper of negative 2.83. Then you would leave it standard normal with mean 0, standard deviation 1. And if you do that, you're going to get the exact same answer. Most of you will probably like the last slide better a little bit because it just uses the numbers from the problem. This is like a little extra step, but this is actually really helpful for when we learn about T problems in our next section. So this is the way I'm going to kind of push you towards doing it, even though it's a tiny bit of an extra step. The AP test also really wants to see your test statistics. So this right here, doing a normal CDF on the standard normal, is actually more like encouraged than doing it with the numbers from the problem. So that'll make more sense as we practice even further. So we've talked about our 4-step process right here. And you do 4 steps on significance tests, just like you do 4 steps on confidence intervals. And like I told you guys last chapter, there's a lot to keep track of at first, but the more you do these, you'll get so good at them and so comfortable with them that you will actually really like these kinds of questions. So there's what the 4-step entails. We're just going to jump into an example and see what's going on. So this example is going to pop up later in the 9.2c note. So I will reference this example again. But what we've got going on is there's a potato truck, a potato chip manufacturer, and they are looking at shipments of potato trucks. So they're bringing in all sorts of potatoes, and then they're looking at these shipments to see if too many of the potatoes are gross. They have blemishes, they're not going to make good chips, whatever else is going on. And the threshold, or the line in the sand, that this company says, they say, hey, if more than 8% of the potatoes in this truck are bad, we're sending it back. We don't want this truck. This truck is garbage. Get out of here. Send us a new truck. So that's kind of their level. We'll tolerate some messed up potatoes, but if it's more than 8%, get out of here. We don't want you anymore. Okay? So they are not obviously going to check every single potato in the truck. Picture a giant semi-truck full of potatoes. They don't have time to go and check every single potato and make sure it's cool. What they do is they take a random sample and they use that to guide their decision. Okay? So it's a way of using statistics in real life. We don't have time to test all of the potatoes. So what they do is they end up taking a random sample of 400 potatoes, and they find that 10% of the potatoes have blemishes on them. 10% is higher than 8%. But here's the thing. They didn't test all the potatoes in that giant truck. They only tested 400 of them. So again, think about me and Larry arguing earlier. What's going on now, instead of me and Larry, it's me, the inspector, versus potato truck driver. I'm saying, hey, we got a 10% right here. That's higher than 8%. This truck is probably bad. Potato truck driver is like, nuh-uh, it's 8% or lower. You just picked an unlucky sample. So this is where we use statistics to figure out which one of us is more likely to be right. So problems like this will not always say, oh guys, do a 4-step, do a significance test on this problem. What we're doing is it just says, is there convincing evidence? Convincing evidence, that phrase, should signal to you guys, do a 4-step for this kind of problem. And what we're doing here, we're not estimating what percent of the potatoes are bad. If we wanted an estimate, like an interval, it's a confidence interval time. We're just making a verdict. Hey, this is my decision. This truck is bad, or this truck is not probably bad, and I'm going to let it in. So we are going to do a significance test. When you need to make a verdict, you do a test to figure out what your verdict should be. So your first step is going to be to define your hypotheses and define your variable as well. The variable that we care about in this problem is going to be P. It's a percent problem. P is going to be the true proportion of potatoes in the truck with blemishes. And I am the inspector in this truck. I'm going to let the truck in unless I see, hey, this truck is bad. The status quo for this problem is come on in, truck. We're going to let you come in and just drop off your potatoes unless you're a bad truck. Then we send you away. So our null hypothesis in this problem is going to be status quo. We allow up to 0.08 of our potatoes to be bad. And if there was exactly 8%, we would let the truck on through. So you go in, status quo is the truck is coming in. If you're a big manufacturer, you're not sending away tons of trucks. Like that's holding up your production. It's making the potato truck people mad. It's just, you're going to let the truck in unless there's convincing evidence that the truck is bad. So my job as the inspector, I am looking for evidence that that P is definitely bigger than 8%. Okay, so this is my hypotheses set up for this problem. Let's go ahead next and define or check our conditions. Before we can do our test, we need to make sure our conditions are satisfied. It is a random sample of 400 potatoes. So that's good. 400 is less than 10% of all potatoes on the truck. And I need to check my NP N1 minus P. You need to do that with the value from your null hypothesis. So I would do 400 times 0.08. And 400 times 0.08, I should know that, is that 32? It is. So that's greater than or equal to 10. And then I would do 400 times 1 minus 0.08, which is actually 0.92. And that is 468, also greater than or equal to 10. That means your distribution is approximately normal and we can move on. So I've established my distribution is approximately normal. It's time to actually do normal CDF stuff. Now we could do it with the numbers from the problem. If we did it with the numbers from the problem, we would be centered at 0.08. And we would be figuring out how rare a 0.10 is. That would be our basic setup, and we would do our little standard deviation formula. But like I said, AP Stats pushes you guys in the direction of doing it the z-score way instead. So what I will do is I will find my test statistic. The test statistic for this problem, I'm going to take my statistic. I got a 0.10. Minus my value from the null that I was supposed to get, which is 0.08, over my standard deviation. And I'm going to do that with my HO value plugged in. So 1 minus 0.08 over a sample of 400. And I would just calculate what that guy is going to equal. So I have 0.08 times 1 minus 0.08, sample of 400. When I do that, my top is a 0.02. My bottom, if I do all of that, is like 0.01356. And if I actually divide those out, I got 1.47. Okay, this is my z-score. So I want to know how rare a z-score of 1.47 is. This is now a standard normal problem, centered at 0. 1.47 would be like here. And then what I'm going to do is I'm going to set up a normal CDF. My normal CDF is going to have a lower of my test statistic right here, 1.47, it's going to have an upper of big number. It's going to have a mean of 0, and it's going to have a standard deviation of 1 because I'm using standard normal here. And if you actually type these in, 1.47, you end up getting a p-value of 0.0708. So the area that you get when you do your normal CDF is your p-value. All right. Let me keep this right here, but I want to show you guys again what I basically did with the numbers from the problem. This would be the same thing as if I centered it at 0.08 and I found the area from 0.10 and above. In terms of my potato truck example, what this basically found out is if the truck has 8% bad potatoes, that's the cutoff, getting a 10% has a probability of happening of about 0.07. Okay? So basically what that's saying is if the truck is actually okay, there's only about a 7% chance of getting a 10 in a sample like this. When you do one of these problems, I actually left this out, and I'm going to go back and add it right now. Before you conduct your significance test, you need to say for yourself, what alpha are you willing to use? What level of evidence is going to be enough to convince you? And you actually need to do that before you run your data and get a p-value. If they don't specify in a problem like this, 0.05 is the most common cutoff, but they can use 0.10, 0.01. Sometimes the problem tells you alpha, but if they didn't, and they didn't do that here, just make up your own. We're going to go with 0.05 because that's the most common, and I should have done that before I looked at my p-value right here. Okay? So that's what's going on. If the truck is actually cool, there's only about a 7% chance of getting a 0.10. So what does that mean? Well, probably this truck is bad. It's probably a bad truck with too many bad potatoes in it. But there's still a 7% chance that, oh gosh, they were telling the truth. It is a good truck, and I could send it back by mistake. So that is too high of a risk level for me in this problem because I set my convincing level at 0.05. This is too high of a p-value. So I'm not going to send the truck back, even though it probably is a little bit too bad in terms of the potatoes. So I'm going to clear this so I have a little space and write my conclusion for this problem. All right, so I got my little script right there. The nice thing about this is we've already practiced in last section how you write a conclusion. So this is just give the script for p-value too high, p-value not high enough. I want to focus while you guys are getting that down and everything on the conceptual idea again of what's going on. Probably this truck is bad. There's only a 7% chance that we could get a 10% if the answer is supposed to be 8%. So it's kind of like in real life, like you can tell sometimes maybe you're talking to somebody and you're pretty sure they're lying to you. Like you think they're not telling the truth on something, but you're not quite sure enough to call them out on it. You know, you're pretty sure they're lying, but you don't want to be wrong because then you would just look like a real jerk and your evidence just isn't quite good enough. If I'm an inspector and I send back this truck, get out of here, buddy, and it turns out the truck was telling the truth, I'm going to be in trouble. My boss is going to be mad at me because now they don't have potatoes to make chips out of, and it's just a whole big thing. At the same time, let's say instead of 10% bad potatoes, they come in with like 20% bad potatoes in my sample. Now that evidence is so strong that I'm like, come on, guy, you're not 8% like you said you are. Get out of here. If somebody tells you a ridiculous lie, you're going to be like, you're wrong. You're going to call them on it. Where if somebody tells you like a lie with a little bit of a gray area, and it's not to say that truck driver has to actually be lying maliciously or anything, but depending on how crazy what they're saying is, you're more likely to actually call them on it. So that's the idea right there. All right, the last thing I need to do in this lesson is show you guys where the button is on your calculator so you guys can do it the shortcut way if you so choose. We're going to go to the same menu we've been using already, which you guys should be pretty familiar with. We go to Stats and then over to Tests. I told you guys last chapter this is going to be like our new favorite menu for second semester. And the option we're going to use this time is called a 1 proportion z test. That's in comparison to what we did last chapter, which is a 1 proportion z interval, because we were doing confidence intervals. Well, now we're doing significance tests, so we just choose the test version of what we already did. After you choose that option, you're going to have a bunch of stuff that you got to type into this problem right here. So let me show you what this all looks like. I kind of spoiled it by having it typed in already. PO is the HO value for your proportion. In this problem, our HO was 0.08. And then for the X and the N, remember that in these problems here, the X has to be a whole number. If you put a decimal in there, like if you try typing 0.10 in there, it's going to tell you error on the calculator. What you need to do, in a sample of 400, we got a 10%. So we just need to do easy math and figure out what 10% of 400 is. 0.10 times 400 is a 40. So that means our fraction is going to be 40 out of 400. Round it to a whole number if it is a decimal, because you cannot have decimals up there. For this next line right here, it's asking you which direction your inequality goes on HA. We had a greater than alternative hypothesis for this problem, and then you just hit calculate. If you do that, it's going to spit out a little bit of info right here. So let me tell you what buttons you need to hit on the calculator. So you have that. What we did is we went stats, we went tests, and we chose number 5 for this. For the actual work you would need to show on your do step, you need to give the name of the test. The name of the test was a 1 proportion z test. You need to make sure you give the test statistic. We got z equals 1.47. And you need to make sure you give the actual p-value. Now on the calculator here, be careful. The calculator writes down just p right here. This p is supposed to be your p-value, but don't write p yourself because p is taken in our class by proportion. So even though it says p equals 0.0701, I am going to write that as p-val. That's what that represents, 0.0701. So this is all you need to include: the name of the test, your test statistic, and the p-value. And then you can just make your conclusion the same way as before.